Okay, so let's go over the worksheets on using Gauss's law to find the electric field for simple geometries. And we went over in lecture last time a very small body with charge Q on it. And so we're going to extend, and we drew an imaginary sphere around that, concentric with that small body. And this is called a Gaussian surface. The Gaussian surface is an imaginary surface, and we use it to accumulate the flux flowing through it and thereby figure out how much charge is enclosed. So we're using, in that case, Gauss's law. The flux of the electric field through that surface is 4 pi times the charge enclosed. Okay, notice, by the way, in my lectures and in the homework solutions, I use the Cgs system of units. I guess I should discuss that. So the textbook is written using a K that he carries around in his equations. That gives the option here of choosing, as he discusses in the book, one of two common systems of units, CGS or SI. So in the CGS system, K would be 1, and the SI system, K is 1 over 4 pi epsilon naught. So you can choose your system of units, go to the equation, and choose that. CGS is preferred by theoretical physicists as a cleaner system, a simpler set of units. SI has historically been used more by engineers, maybe by scientists in the early days. As the understanding of electricity and magnetism developed, it became preferred by physicists to use the CGS system. But if you want to talk to engineers or even some physicists, they'll want to work in the SI. So, of course, in the mechanics, really there isn't much difference between them. CGS uses centimeters, grams, seconds. SI uses kilograms and meters in seconds. In electrodynamics, there's more of a difference between them than simply that. The unit of charge is different in the two cases. And so you have different units for charge. And the equations, as I said, are much simpler in the CGS system. You don't have to carry around this 1 over 4 pi epsilon naught all over the place. If you see epsilon naughts or mu naughts, you're working in what you're seeing is in the SI system. So I'm going to, in my lectures, I've already been doing it, just didn't talk about it, using the CGS system. K is 1. And all my solutions are that way. He carries it through in the textbook for quite a while, where you have the option of just the equations are written with K, and then when we get into magnetism, there's another choice of units, or another way of reflecting the same thing. So in any case, what I've chosen is K equals 1 here, the CGS system. Okay, so in this equation, for example, Gauss's law that I've written here, there's not this is Gauss's law written in CGS. You may have noticed, perhaps you did. Without that, you have a K on the right-hand side. Okay, so now we did this problem in the for the simple charge here, and we found that the electric field was Q over R squared and then points radially outward for the single charge. So we used that. Gauss's law to find Coulomb's law. Okay, so it's a way to touch back to what we started with, this Coulomb's law. Gauss's law works because the electric field generated by a point charge falls off like 1 over the square of the distance. So this Gauss's law is a reflection of the 1 over r squared force law. It's just not as obvious when you write it this way. Okay, now the problem you had in your homework was to consider a charged sphere. So we're going to take a sphere of some radius r1. First we just do a single sphere, just radius r, and we're going to put charge q and distribute it uniformly over the sphere. So this is a little bit different than this problem, of course, because now the charged body is itself a spherical shell. So the charge has been distributed uniformly over the shell. Okay, so the argument is basically the same, though, and I want you to pay attention to the symmetry argument as you go along. Remember, Gauss's law is helpful if there's a lot of symmetry, and this is still a rather symmetric situation. So we would create a Gaussian surface but we have the choice of creating a surface either that's outside or inside that sphere. Okay, now the charge enclosed, if the radius is outside the sphere, then the charge enclosed is the charge that we place on the sphere. If the radius is inside the actual sphere, the real sphere, then the charge enclosed is 0. But you can go through the same argument with symmetry and so forth, and therefore find out that the electric field is 0 if you're inside the sphere, and is Q over R squared R hat if you're outside the sphere. So it shows that the electric field inside of a charged sphere is 0. This is similar to what we found when we looked at the gravitational field. We didn't talk about this very long. When we were considering the gravitational field last semester, gravitational field inside of a spherical mass shell, a massive body made out of a spherical shell, and you're inside, there's no gravitational field inside, and there's no force because of the gravitational interaction inside. It's the same thing is happening here. Now you have to also remember this when we're constructing this shell. We put the charges in place on the sphere, and we don't let them move, right? So you have to keep that in mind. Yes, sir, Mr. Luke.
Is the field just Q over R squared R hat if the little r is equal to big R as well?
Okay, so in that case, it's not really well defined, because what we've done mathematically is to construct things that don't exist physically. Right? So we have here constructed an infinitesimally thin shell, and we've distributed the charge over that. Such a thing does not exist, and that's really what's creating that question. So really what you would have, of course, is something that has finite thickness to it, and then there would be a gradual shifting from outside to inside. And you have, but again, the argument would apply there that the electric field would depend on how much charge is enclosed by the Gaussian sphere. So there would be, but it would be in a physical situation a more gradual shift. Does that answer your question?
Yeah.
Okay. And that's an example of an excessive abstraction. And that happened even here when we were considering that case. We don't have infinitesimally small bodies with charge on them, right? There is no such thing as a point-like source in the real world. It's a mathematical abstraction. The real world does not have such things. Okay. Okay, the physical world. Okay, and now you can consider that, okay, let's see, you can consider that same extension here. Let's suppose we have two concentric spheres, and we have two different charges placed on them. Plus Q on the inside sphere, minus negative Q on the outside sphere. This is R1, this is R2. Now we've divided space up into three regions, and we want to find the electric field in each of the three regions using Gauss's law. And again, this is very symmetric. There's a lot of symmetry in this, and we can use Gauss's law to find it pretty simply. And we could also just use the superposition principle. So the argument using Gauss's law would be to construct a Gaussian surface here, and we have a choice here of whether it's, inside. We have three different possibilities here. It's R is inside the inner radius, or the radius of the Gaussian surface is in between the two physical spheres, the two real actual spheres, or the radius is outside. So we have three different regions. And these charges are balanced here. So when we construct the Gaussian surface out here, the enclosed charge is 0. So the field outside would be 0. And likewise, the field inside is 0. So there's only one region where there's any electric field, and in this case, it would be Q over R squared R hat. So it's pointing radially outward in that region in between because it has a positive charge inside. Now you could construct the same thing by considering a superposition of the electric fields. You have the electric field in the previous problem. We did the electric field by one sphere, this electric field only outside, and with a positively charged sphere, the electric field points radially outward. Well, if we had had a negatively charged sphere, the electric field would be non-zero outside, but it would be pointing radially inward. And so you could take those two and superimpose those fields and get this. Right? You get a superposition outside. You get a superposition of the two electric fields, one pointing inward, one pointing outward. They cancel out. And so the outside, you could understand why the electric field is zero outside. And so you could superimpose. So you can construct it either of two ways. You can go back to Gauss's law and do it again, or you can take what you know already and use the superposition principle and get it that way. Does that make sense? Puzzled about that last part about superposition? Okay. So this inner, ooh, how did I do that? I didn't know that was possible. Ha! Okay. It didn't reconnect the arrow there. That's interesting. Okay. Stuff I didn't know I could do. Oh, no, that wasn't, that's right. That was not connected in the first place, was it? Okay, that's a really big eraser. Okay. So this inner positively charged sphere generates electric field outside of it, right? Out here as well. But the negatively charged sphere generates an electric field pointing radially inward of the same magnitude. And those cancel out, so there's no electric field outside. Right? Now notice that the distance involved here, this r, is the distance from the center of the sphere. This from here. Not the distance from the shell, but the distance from the center of the shell. It's as though all of the, notice this, going back to this case here, it's as though, in this case, the electric field outside of the sphere is the same magnitude as this case, right? You can put all the charge at the center, and it generates an electric field that looks like that. And if we have a charged sphere, if you're outside the sphere, it has the same magnitude as though the charge were concentrated at the center. Okay, all of which are consequences of Coulomb's law or Gauss's law. Okay, so then the same thing happens here for the cylindrical case. In fact, I think I've written here described here a cylindrical shell, so the charge is actually distributed on the cylindrical shell. I actually did a wire in class, but now let's give that finite radius. So there's charge on the outside of this cylinder, but not on the inside. And we would construct a Gaussian surface. I did this in class last time. We constructed a kind of cylindrical surface, end caps here, and then the what we called the belt here. And so it's the same argument. The electric field points radially outward by symmetry. I went through that argument last time, so I won't do it again. Points radially outward. So there's no flux through the end caps. There's only flux through the belt. And it's the same. Really, it doesn't matter what the radius of the wire is as long as you're outside the wire, outside the cylinder. So the electric field in this case, by application of Gauss's law, points radially outward here. And so it's, so I'm going to discuss this notation here. This is notation that he uses in the book here. So let's look at this here. This is the radius of the cylinder. R rho here is the distance, is the radius of the Gaussian surface. So it's the distance from the axis. And rho hat points outward. So rho hat is in the direction, rho hat is this way or this way, depending on which side. So looking along the axis, rho hat points radially outward. Like that, rho hat. So it's the two-dimensional vector that points radially outward from the center. Okay, now you could again, when you have the coaxial cylinders, that's the next problem. Consider a coaxial cylinder, which is a combination of two cylinders. They're concentric, one inside the other. And now I'm going to put opposite charges on them, plus Q and minus Q, or the other way around. I can't remember here what I constructed. So you can, again, apply Gauss's law with the same surface. You see there are three different regions. They're inside both. There's in the transition between the two cylinders, and then there's outside both cylinders. So you could use the superposition principle, or you could just go through Gauss's law of construction again. And the solution then, there's no electric field outside. There's an electric field in between, and no electric field inside. And this is one reason why coaxial cables are used, because they you can carry current on them, but they don't generate much electric field outside of the coaxial cable. The electric field is confined to the region between the two elements of the coax. For reference to coax, this is the way a coaxial cable is constructed, like this. Okay, so then we go to, notice that the field drops off like 1 over the distance from the cylinder or from the wire. So it's 1 over r squared from a point source or a spherical source. It's 1 over distance from a cylindrical source or a wire. And remember, we're far from the ends. We keep making that caveat. We're far from the ends of these things. And finally, in this homework, we looked at a plate. Let's take a plate, huge plate. We distribute Q evenly over this surface. All right, and going back here, remember this, what lambda is? Lambda is the charge per unit length. So we put a total charge Q over this wire, long wire of length L, distribute the charge uniformly over that cylinder. So lambda is the charge per unit length along the cylinder. Okay, we're going to do something here similar. Oh, how did I do that? I need to do this. We're going to put here something similar. We're going to take a great big area. We're going to put charge Q distributed over that area so that, and so then we talk about the charge per unit area, this is sigma. So we have 3 different kinds of charge density. A volume charge density, rho, which we designated as rho, is common. Charge per volume. Then we have a charge per area here, and we have a charge per length. So just convenient ways of describing the density of the charge. Now we construct a Gaussian surface here that straddles the surface here. So it goes below here. So it could be a cylinder, for example, straddles the plane. So if I'm looking end on or edge on here, my Gaussian surface looks like that, right? It has end caps on both sides, and we could have, really doesn't matter the shape so much as it has flat surfaces that are parallel to the plane. Okay, and then we go through the same argument again, but now the symmetry argument will give us that the electric field must point either radially outward, straight outward, or straight inward. Can't have any parallel components because we can rotate the plate around. Any parallel components would rotate with the plate, but there's no reason that should have one preferred direction over another because there's rotational symmetry. So there can't be any parallel components of the electric field. It can only point radially outward. Okay, and then the amount of charge enclosed is going to be sigma A, where A, I guess I should use small a. Sigma A, which A is the area of the end caps. And the flux coming out, there's no flux coming out through the belt now, right? There's flux only from the end caps. You have 2 end caps, 2EA, and so that tells you then that the electric field pointing straight out, make sure is 4 pi sigma pointing out. So if this is the z direction, then this would be, I'm sorry, it's 2 pi, excuse me, 2 pi. That looks better. 2 pi z hat times The SIGIN of Z meaning it points up or down depending on which side of the plate you're on. Okay, now you can do the same argument. You have parallel plates. You could have two parallel plates with the same charge, two parallel plates with the opposite charge. You can figure out what the electric field is in between. If the parallel plates, two parallel plates, have opposite charge, plus Q and minus Q, then there's no electric field outside. There's an electric field inside, which points in this direction. And the magnitude of the electric field in here is 4 pi sigma, where sigma is the charge divided by the area of the plates. And it points from positive charge to negative charge, right? If the electric field goes in that direction, from positive towards negative. Any questions about that? These sorts of simple arguments are really handy, but they only work in highly symmetric situations. But they're really nice to see. Gauss's law works in any case. It's just that these integrals, like this integral here, is only simple when we have a really highly symmetric arrangement of charges. You know the electric field is really simple behavior. So Gauss's law is always true. It's always valid. It's just that it's not so easy to apply unless you have really simple symmetry. In that case, then you can really see how nicely it makes a really quick way of figuring out how the electric field should behave. Which is why I make you go through this, because it's kind of neat to see that. So any questions about electric fields? Yes, sir?
So what do you mean, like, when you say you create a Gaussian surface?
Yeah, it's in the imagination. So you have obviously some physical arrangement of charges, but Gauss's law holds here. This surface integral holds for any surface, any imaginary surface that you could construct. So you're free to draw any imaginary surface. But in these cases, there's obviously, because of the symmetry, that integral is easy if you draw a surface that conforms to the symmetry of the physical bodies that exist. Then that makes the integrals trivial, almost trivial. But the Gaussian surface is not a physical surface, it's simply an imaginary surface. But you know that if you were to evaluate the flux coming through any surface, any imaginary surface, it must be related to the charge enclosed. Does that make sense?
Yeah.
Does that help?
So, like, what do you mean when you create a Gaussian surface for two concentric shapes? Like, what do you mean that surface in between?
You mean like the two concentric spheres?
Yeah.
Well, I want to choose a spherical Gaussian surface because it conforms to the symmetry of the physical surfaces. So I want to conform to that symmetry which is given to you by the physical source, the physical bodies that are present, the bodies that are present. And so I choose a spherical Gaussian surface to conform to those. And by symmetry now, when we went through this, the electric field will point either radially inward or radially outward because of the symmetry, and it's uniform over the Gaussian surface. So that makes that Gaussian integral, that surface integral, makes it easy to do. It's just the magnitude of the electric field times the area, plus or minus. So that's why we choose a Gaussian surface that we do. Now you could choose any Gaussian surface and Gauss's law will still hold. It's just that the evaluation of the integral is not so easy anymore. And so that's why I pull out these particular problems. So the other thing that it illustrates, the other reason for doing this, is that it illustrates the three different kinds of forces, electric quit. Here we go. Electric field goes like 1 over r squared for either a point source or spherical charge. E goes like 1 over the distance for a cylindrical or a wire. Or E, it goes like a constant for a planar geometry. Yeah. And so the electric field, you remember we got these results before when one of the first homeworks was to look at how the electric field falls off, weakens as a result of the propagation outward from the source. Okay, so this agrees with what we had before. But I want you to remember this because it's a convenient way for understanding how to generate electric fields of different kinds. If you want a uniform electric field, you'd want a planar geometry. You'd want two parallel plates, for example. then you can generate between them a uniform electric field, or at least it's uniform as long as you're away from the edges. And that's a parallel plate capacitor. You'll see that used in electronics a lot. Or if you want to, you could generate electric fields that have different non-uniform strengths by choosing the geometry appropriately. Okay? Okay, now let's go on to the electrostatic potential. What is phi? Well, let's go back to what is E. What is E? What's the electric field? I should say, what is the electric field? Not what is E, but what is the electric field?
Property of the planet.
It's property of the planet in what category? Power, which is a quality. It's caused in the plana by a charged massive body, and it propagates outward from one part of the plana to another part until it's possibly, so that field exists in the plana. The electric field exists in the plana, regardless of whether there's another charge to receive it, another charged body to receive it or not. But if I place another charged body in the plana that has this field in it, now it will experience a force on it. And remember that force is then, so this would be the force on a test charge. It's going to be the charge on that test body times the electric field at that place. Okay? All right, so what is phi? Phi is the electrostatic potential. And it has the same relationship to the electric field as the potential energy does. So there's a potential energy associated now with putting this test body at that place. And usually what you might do, for example, is bring the test body in from far away and bring it in close. And that gives you the reference point then for the potential energy in that case would be at infinity. And you bring it in close. Okay? So if I have two bodies, Q1 and Q2, the potential energy, there's a force existing between these bodies, right? And the potential energy that's associated with that arrangement is simply the product of the charges divided by the distance between them. Okay. Now, what is the electrostatic potential? Well, I could go back and I could see here, looking back at the force on the test body is proportional to the charge on the test body. And how would I determine what the electric field is? Well, I would go and put a test body in and see what is the force on that. And then I would divide that force by the charge, the known charge on the test body, and that would determine for me what is the electric field that was there before I put the test charge in. Okay, that's how I would go to determine that there's an electric field. I put a charged body in there, I see what force is present, and I notice that the force is proportional to the charge that's on the test body, so I can determine what the electric field was at that place. Same thing would happen then for the potential energy. Let's see, so let's go back here. Remember that the force is the negative gradient of the potential energy. And so let's go back and consider that we have a charge Q here, and then we have a charge on a test body. This is Q test. And so the potential energy then is this, R from the test body. R from Q, okay? So I could measure the potential energy if I put this test charge in. And I could find out what an associated quantity called phi, which would be the potential energy per charge on the test body. So if I take the charge on the potential energy on the test body and divide by the charge, this is something that doesn't depend on the test body. And it is a property of the plana, and I call it the electrostatic potential. Now notice the wording is a little bit funny. It could be a problem because we use the word potential here. Electrostatic potential is not the same thing as potential energy, right? The relationship is given here in this equation here. The electrostatic potential is a potential energy per charge. that would be present if I put a test body in there. But the potential, electrostatic potential exists whether there's a test charge or not, just like there's an electric field. And you can see here the relationship then between the electric field and the electrostatic potential is this. So in other words, we have this kind of parallel relationship here. The force and the potential energy exist only if I actually put a test body in there, but the electric field and the electrostatic potential exist even if I don't put a test body in there. It's a property of the plana. So phi is another way of specifying the condition of the plana. It's a further specification of the state of the plana. In addition to the electric field, phi tells you more about the state of the plana. There are a couple of ways of seeing that. If I want to generate an electric field, there are lots of ways I could arrange charge to generate that electric field at that place. Phi, by giving phi, gives you a little bit more information about the arrangement of charges that I would need. And another way of saying that is, if I have phi present, if I have an electrostatic field present, remember the electric field is the gradient of the electrostatic potential. So if I were to place a charged body, it would sample the region around it. That's what the gradient is saying. It would sample the region around it and cause, therefore, it would tend to move towards, a positively charged body would tend to move towards lower electrostatic potential. Okay? So, in other words, test charges that have plus Q tend to move towards lower phi. But opposite test charges would move towards higher phi. In other words, if you place two charges of opposite sign in this region, they'll move in opposite directions. If you put a plus Q and a minus Q here, the plus Q would move in the direction of the electric field, which goes towards lower phi. The negative Q would go in the opposite direction, because the force on it would be the opposite force. So it's going towards higher phi. Okay, and the other way of remembering it is that the potential energy is the product of the potential energy of a test body is the product of the charge on the test body times the electrostatic potential. Okay, so this turns out to be really pretty convenient to use, aside from telling you more about the electrostatic condition, more about the condition of the plana. It's actually also convenient because the electrostatic potential generated by a charge Q in the plana at a distance r from it is just Q over r. Really simple. So expressed in Cartesian components, it's this. And so I see my solution didn't have this. You were supposed to, from this, find the electric field. So let's take the negative gradient of this. And that's not in the solution I see here. I need to update my solution, send it back out to you. But let's take the gradient of this. Electrostatic potential. So we have the derivative with respect to x of this thing, kind of complicated looking. X, y, and z are treated as constants. They're not zero, but they're treated as constants. We need to use the chain rule here, so we take the derivative of the 1 over the square root. So that gives us a minus 1/2. Remember, the square root is a negative 1/2 power. So x squared plus y squared plus z squared to the 3 halves now, right? We lower the power. It's already negative 1/2, so now it becomes negative 3 halves. And then we take the derivative with respect to x of the thing that's inside here, inside of the square root. Okay? You know, lots of possible ways to get signs wrong, factors of 2 wrong, all kinds of details that you've got to learn how to deal with. Okay, and now that derivative with respect to x, well, y and z are treated as constants, so that's just the derivative of x squared. And so we get this derivative gives 2x. Okay, so that derivative gives then negative x over x squared plus y squared plus z squared to the 3 halves. Okay, and then now you can see what the other terms come out to be, because the derivative with respect to y leaves a y in the numerator, the derivative with respect to z leaves a z in the numerator. And so the electric field then, and there's another negative sign here you got to remember, there's that negative sign there as well as this negative sign. So it comes out to be x hat plus y hat plus z hat divided by x squared plus y squared plus z squared to the 3 halves, and then there's a q out front. And that is the electric field. You should recognize that as the electric field in Cartesian form generated by a charge at the origin. We could write this also as r over r, the vector r over the distance q. Right, we've done that. Okay, so that works. That gives us the same result as what we had before. And now it's just an exercise in writing the electrostatic potential for different charges. And I'll leave that to you for you to study. It's just a matter of being careful. So, but it is a good chance for us to go back because and review something here because we need to remember this. If I have a charge Q at position r prime and I want to know what is the electric field over here, right? The recipe is very simple. The electric field then is just Q in Cartesian form. You need to remember this, and then it's all over the sum of the squares of the differences of these components. This is like what I just wrote, except it's now I've shifted the, oops, that's 3 halves. I've shifted the origin, so the charge, it's just charge, so the charge is not at the origin, right? You need to remember how to do this. And we had some exercise problems last night during the recitation, and I think some of you are still learning how to practice, still practicing how to do this. And if I put 3 or 4 charges in there, and then you want to try to figure out what the electric field is, it can be a bit of a challenge because there's a lot of x's and primes and signs and stuff, right? So it can be a little bit of a challenge. So you need to practice that and make sure you can trust the recipe. The recipe will get it correctly, regardless of whether the charge here is positive or negative and so forth, as long as you make sure that you get these things right. Okay? Okay. Any questions about electrostatic potential? Okay, so now for Monday, you're going to generate a catalog of the electric field and phi field, electrostatic potentials, for some simple geometries. You just did that. You've got the basic elements of that catalog for in that worksheet on Gauss's law. Right? The geometries that you're going to consider are the ones that you did in that previous worksheet. So that is a point charge or a charge, a spherical shell with charge on it, or a cylinder with charge on it, or 2 concentric cylinders with opposite charge, or plates, maybe 2 plates with opposite charge, whatever. You're going to construct a catalog just so you can have in your mind these different geometries and the electric fields associated with those, and the electrostatic potential for each case. So the electrostatic potential for a point charge, so-called point charge, which is a very small body, right? The electrostatic potential goes like Q over R, right? Okay, so now what do you think? What would be, let's take a wire. We put charge on this wire, so we have a charge per unit length, lambda. What is the electrostatic potential outside of this wire, a distance rho from the wire? And we're going to say it's really far from the ends again. Let's don't consider end effects. In this region, remember, the electric field looked like, what was it, 2 lambda over rho hat. So what does the electrostatic potential look like? Remember, the electrostatic potential is the derivative of phi, it's negative gradient of phi. So if E goes like 1 over distance, what is phi? No, the other way around. I know, you have to remember. So you want, what is the derivative of what goes like 1 over distance? Natural log. It's a natural log. So this is going to go like the natural log of rho. Be proportional to 2 lambda. And we've got a negative sign in there, right? So I'm gonna let you figure out the sign here. What is the correct sign here? So the electrostatic potential goes like a logarithm of a distance. Okay, and the other case was a plate. And let's consider the case of 2 parallel plates with opposite charge to make it simple, plus Q and minus Q. The electric field points downward like that. We say the electric field is uniform in between the plates. So how does the electrostatic potential look inside here?
2 rho.
Let's see. So we have here a sigma. Remember, it's a charge per unit area. And the electric field in between goes like 4 pi sigma. In this case, it was negative z, right? It was downward. If z is this direction, z hat. So it was that inside between the 2 plates. The derivative of what is a constant?
X.
Right. Yeah. In this case, it would be proportional to z, right? The electrostatic potential is just is linear from one plate to the other. It's just linear ramp from one plate to the other. And which way has higher electrostatic potential? Remember, the positive charges want to go to lower electrostatic potential. So which way is higher electrostatic potential? The positive charges want to go in the direction of the electric field, so this should be the lower phi, and this should be the higher phi. Electric field goes in the opposite direction of phi. It goes towards lower phi. So the electric field's in that direction. Okay, and then phi will be linear. So I'm not going to spell all of your homework out for you, but just hopefully you get through this. So you're going to generate a catalog of E and phi for these different geometries. And it's just, set up. It may take 2 or 3 pages for the geometries, but it's all basically we've done. It's just trying to put it all in one place so you have it in your mind, so you can kind of get your mind wrapped around this, how the electric field looks in different geometries and how the phi electrostatic potential looks for different geometries. Okay, we're also going to spend just 2 days on circuits, electric circuits. And that's also part of your homework. On Monday, you're going to start doing that. You're going to read up on electric circuits. And the concepts that we've generated here between the electric field and the phi field, remember what we're focusing on here is the electrostatic condition. So now we're relaxing that a little bit because we're talking about circuits, we're talking about moving charge around. So now we're relaxing that a little bit. But again, the electrostatic approximation says that you don't need to consider the time that it takes for the signal to transfer from one place to the other. That propagation time is so fast you don't need to worry about it. So we're working in the electrostatic approximation, which means things can move around, but the distances involved are short enough that you don't need to worry about the delay because of the propagation time. So the speed of light is so fast, and your apparatus, whatever your system you're considering, is small enough that you don't need to worry about how long it takes for light to propagate from one side to the other of your apparatus. If you're doing a tabletop experiment and you have ordinary electric circuit, you don't need to worry about the speed of light. Things happen slow enough. Okay, so we're going to consider now 2 different, well, really something here, a conductor And a conductor is now a substance that allows the parts that are charged to move around freely inside. And you consider that in a conductor, there can really be no electric field present, because as soon as any electric field tries to enter into a conductor, it will rearrange its charged parts in response to that, so that there aren't any electric fields present. It will screen out any charges, okay, any electric fields. Okay, so we'll consider without really thinking about how these things work, a battery, which generates an electrostatic potential from one end to the other. So the battery will generate an electrostatic potential. Stop. Okay, I think I didn't turn it off. Excuse me just a second. I'm sorry. I have to do this or I'll never stop talking. Right, okay. No, I didn't do what I wanted to do. Okay. All right, so that generates an electrostatic potential. So that means that up here, there's a higher electrostatic potential than down here. And the battery maintains that, in spite of the fact that the parts in here want to flow down in electrostatic potential. They want to flow downhill, but they can't. The battery prohibits that. It generates this electrostatic potential and maintains it, and keeps the charges going, prevents them from going back against that electrostatic potential. Okay, so then we consider that this wire that connects these things is a conductor, and that the charge flows freely inside of the wire, and then it encounters, here we'll wrap this up, if we place inside here, inside of this wire, inside of the circuit, a resistor. So in a resistor, there is imperfect response to an electric field. So an electric field can exist inside of a resistor, and charge will flow in response to that electric field. So if we look at this conductor here, this electrostatic potential has been conducted by the conductor, so the electrostatic potential is the same here as it is here. And also the electrostatic potential is the same here as it is here, because I've connected the wire to it. They're connected by perfect conductors. These are idealizations. No material is a perfect conductor, but we idealize it when we're considering these things, that there's a perfect conductor. So what I've done here is to create an electrostatic potential across this resistor. A resistor is a material that does not have perfect conduction. Really, all materials, very few materials have perfect conduction. Superconductors have perfect conduction, but at room temperature, virtually everything has some resistance. But we consider it an idealization here. So we have a really good material that has a really good conductor, like copper, for example, is a really good conductor. Water is pretty good. A resistor would be something else. An insulating material like plastic would be a really good resistor. Not much will flow, okay? So the question here is, if now I generate an electric field inside of this resistor. The electric field, remember, is going in that direction. There's an electric field inside of that resistor. This uniform electric field inside of that resistor. The resistor, there's going to be some material and constructed in such a way that we get flow current through this material as a result of having this electric field, and the amount of flow, the current that flows through this resistor, is proportional to the electrostatic potential divided by a characteristic of the material called the resistance. This is called Ohm's law. If I put a greater electrostatic potential, I hook up a bigger battery or a battery with more electrostatic potential across it, I will generate a larger electric field in the resistor. I'll get more current flowing through the resistor. The amount of current flowing through the resistor is proportional to the potential drop across the resistor. So that resistance, R, is a property of not only the material but the geometry of the resistor. depends on everything I've done about how I construct this thing. We won't go into details about that, but you construct resistors. You can construct resistors using the same material, but if you have them in different geometry, arranged in a different way, you'll have a different resistance. So the resistance is a property of how the thing is constructed. If I go to a electronic shop and buy a resistor, get resistors that all have different resistance and so forth. Okay, so if I hook up a battery to a resistor like that, I'll just get current flow as is constructed here. Okay, and you'll study that and the nature of this current, how this current is related to current density. Okay, this is the total current. I is the total current. And we'll talk next time about how that's related to J, which was a current density. But I will say one thing, hold you just for a second longer. You don't know in this circuit, again, whether if the current is flowing in this direction, are those positive charges moving in that direction or negative charges moving in the opposite direction? You don't know. Both will give current moving in that direction. Remember, the current was a product of the charge density and the velocity. So if I have positive charges moving in one direction, I get positive current. Or if I have negative charges moving in the opposite direction, I have the same positive current. So you don't know. And it depends on the materials involved, whether I'm actually getting current flowing here because of positive charges moving in one direction or negative charges moving in the opposite direction. In metals like copper, it's actually negative charges that are mobile.